Hello everyone. Have you ever wondered why Rust doesn't need a garbage collector like Java or C Sharp, yet it still guarantees memory safety? Or how it manages to avoid entire classes of bugs that even seasoned C++ developers wrestle with? The secret lies in a unique concept called ownership. Once you understand this, everything else in Rust, borrowing, lifetimes, references, will click into place. Mastering ownership is like unlocking the true potential of Rust, giving you the power of systems programming with incredible safety. So, what is this ownership? Ownership is the way Rust manages memory. The values we create and use while programming get stored in the memory. Once the use of those values are completed, we don't need them anymore. So we can remove them from the memory and use that memory to store some other values. In languages like C or C++, you have to allocate the memory. And once the purpose is served, you also have to deallocate to free up that memory. So you have to remember to do it. If you forget, your program becomes messy, uses too much memory, or can even crash the program. In languages like Java or C Sharp, there's something called a garbage collector. It's like a robot that comes around and cleans up your mess later. But that robot can sometimes slow things down. To avoid system slowing down, Rust don't use a garbage collector. And to retain the speed, performance, and control of C or C++ without having the headache to allocate and free up the memory, ownership becomes the solution for Rust. This is basically a set of three simple rules enforced on the user so that all these can be achieved. Rule number one: each value in Rust has an owner. Imagine you have a toy and you're playing with it. Now, your friend also wants to play with it. But you can't both play with it at the same time because that could cause a fight or the toy might break. Since you own the toy, and if your friend wants to play with it, he will have to borrow it from you. So then he becomes the owner. You can't use it anymore unless he gives it back to you. So that is rule number two. There can only be one owner at a time. If the friend leaves your home with the toy, that means the toy don't exist in your home anymore. So it is gone. That is rule number three. When the owner goes out of scope, the value will be dropped. Here, your home is the scope in your program, and the toy is the memory allocated in the current scope. So that's ownership in Rust. It's just a way of saying this piece of memory belongs to this part of the code, and only that part can touch it right now. Let's see basic ownership transfer using string. Here, we are creating a value and assigning it to S1. Then, assigning S1 to S2 within the same scope of the main function. What happens here is that the value of S1 moves to S2. So, the ownership of the value belongs to S2, and the variable name S1 is free to use for any other purpose. This is actually a shallow copy where the reference pointer to the value moves from S1 to S2 without creating the value in a new memory location. If you want a deep copy where S2 gets the same value but created in a new location, and both S1 and S2 owns their respective values, we use the clone function. Now, you can see both S1 and S2 can be printed from the same scope without any error. Ownership can also be passed between functions. Here, in the main function scope, we declare a string using the variable s. Then call the function takeOwnership and pass the variable s as an argument. In the takeOwnership function, we are printing the value. Since we are passing the ownership to this function, the value gets printed without an error. But in the main function, if we try to print it after passing the ownership, s is not valid anymore. Hence, we'll throw an error. We can also get the ownership back to the main function by returning the variable using an expression. Here, we just write the variable name in the takeOwnership function without the semicolon, making it an expression. Now the print in the main function will work fine. Ownership applies to all heap allocated data, like vectors or HashMap, and not only just strings. For primitive types like integer, bool, char, or float, instead of ownership transfer, the values get copied in the stack. So, this is how Rust automatically frees memory without using a garbage collector, achieving memory safety at compile time. We also use borrowing along with ownership to share data safely in Rust. But that's the topic of our next video. Don't forget to like, share, and subscribe to the channel before moving on to that one.